Hello everybody. So in this video, we get to have some fun and start our study of series, which is something we're going to be doing for several weeks and is very important. So a series is a sum of infinitely many terms. So however can we untangle such a thing? Let's get started. So here is the setting. We have a sequence. So let's remember a sequence is just an ordered list of numbers that we studied before. And we want to sum up all the terms. And because the sequence that we're interested in are infinite sequences, that means we have infinitely many terms to add together. So you have to do A1 plus A2 plus A3 and so on and so on. We just keep going. So this seems pretty unfamiliar, right? We know how to add up 2 things or 3 things or 100 things or maybe write a computer program to add up 10,000 things, but how can we sum infinitely many things? And before you get scared, this is not something that's completely unfamiliar. For instance, if we think of pi equals 3.14159 dot dot dot, this is only an approximation, right? It should continue. Very embarrassing. What does this really mean? It means that pi is, okay, first it's 3, and then we have the 0.1, and 0.1 is 1 over 10. And then we have the 4, which is 4 over 10 squared, because that's the next decimal place, 4 over 100, 4 hundredths. Then we have the 1/1000, so 1 over 10 cubed. Then we have the 5 over 10 to the 4, and then we have 9 over 10 to the 5, and then so on and so on. It keeps going. So this is actually already an infinite sum by itself. Okay, so let's get started. So what do we mean by a series? A series is just an infinite sum. It's a sum of all the elements in the sequence, A1 plus A2 and A3 and so on. How are we actually going to do that? Right now it's just a formal thing. I didn't tell you how to calculate it or what it means to converge or not. And as usual with calculus, we're going to study something hard by studying something easier and then taking a limit. So we don't know how to add up infinitely many things, but we do know how to add up 2 things or 3 things or even n things for different n. So we do that, we add up n terms and we take a limit. So we would be adding up 100, 1,000, 10,000, so on, and take the limit, and that's going to be our definition of infinite sum. So let Sn denote the partial sum. This is going to be an important thing we keep going back to. Sn is the sum of the first n terms. So if you plug in an n, you calculate a different Sn, you're going to get, say, 100 terms, or the sum of the first 100 terms, the sum of the first 101 terms, and so on. Sn is the sum of the first n times. And for each different n, we have a different number of Sn. If I give you n equals 100, you compute S100. It's the sum of the first 100 terms. If I sub in n equals 101, you're going to sum up the first 101 terms. Sn depends on n, so Sn itself is a sequence. So notice that from the sequence an, we calculated a new sequence Sn. Sn is the sum of the first n terms. Okay, and we just transfer all questions about the series onto the partial sums Sn. So the infinite series sum of an converges, say, to a number s, if the partial sums converge to s. So if the partial sums Sn converge to s, we say the series converges to s, and we write the sum of the series is equal to s. Okay, and conversely, if the partial sums diverge, so if this new sequence diverges, we say that the series diverges. So here is so just to summarize, we say the infinite sum is the limit of the partial sums. So to find an infinite sum, we add up the first n terms, we see what we get, it depends on n, and we take a limit. Notice this is kind of like improper integrals of type 1. When we wanted to integrate to infinity, we replaced the infinity by t, we worked out the integral up to t, and then we let n go to infinity. Here we want to find the infinite sum, so the sum all the way up to infinity. We replace infinity by just n, we add up the first n terms, and then we take a limit as n goes to infinity. So they're kind of similar. So here is a simple example. Let's suppose we have the sequence, which is just 1 for every n. So the sequence is 1, 1, 1, 1, 1. Does it converge or does it diverge? Okay, well, how do we do that? Well, we have to use the definition. A series converges if the partial sums converge. The series diverges if the partial sums diverge. So let's try to compute the partial sums. The partial sums Sn are just the sum of the first n terms. So here is Sn, it's the sum of the first n terms, A1 plus A2 up to An. Okay, this is a particularly simple sequence. All the AIs are just 1, right? This is a sequence which is constant 1. So that means we have 1 plus 1 plus 1 and so on, and we have n copies of them. So that's going to be equal to n. Okay, and then we just ask the questions about the partial sums Sn. So here Sn is n, Sn diverges rather to infinity. Okay, that's exactly what we mean by saying the series diverges to infinity. So every question about the series sum of an, we just calculate this new sequence, Sn, if we can, and then we ask the question about the sequence Sn. So here, let me just reinforce. So summing the series means convergence of the partial sums, not convergence of the individual terms. Here, the terms are always 1. The terms definitely converge. The terms are constant 1, so the terms converge to 1. But the series itself diverges, right? If we sum 1 plus 1 plus 1 plus 1 plus 1, If we sum it n times, we get n. If we let n go to infinity, we get infinity. And it makes sense, right? If we try to add 1 infinitely many times, we would hope that we get infinity. Okay, here's a different type of question. Suppose we're given the partial sums. So suppose we're given a series, we don't know what the an's are, but we know that the partial sums, the sum of the first n terms, supposedly work out to be 2n over 3n plus 5. Okay, then the sum of the series is the limit of the partial sums. So we just take the limit of this sequence of partial sums Sn. In this case, we divide top and bottom by n. It comes out to 2 over 3. Okay, that's the sum of the series, which is 2 over 3. Okay, so all the cases where we've actually computed, or I guess just the one case we've actually computed the series, depends on finding the partial sums. So let's next study a couple of series where we can actually compute these partial sums exactly. So the first one we're going to be interested in is the geometric series with first term a and common ratio r. So if we write out the terms, it starts with a plus ar squared and so on. So clearly the first term is a, that makes sense. And the common ratio is r, means that we get the next term along in the sum by multiplying the previous term by r. So I multiply by r, I get ar, I multiply by r again, I get ar squared, I multiply by r, I get ar cubed, and so on. So the ratio always has to be the same, has to be r, it's supposed to be a common ratio. So let's try to calculate the partial sums. So Sn is the sum of the first n terms. Here the sum of the first n terms is a plus ar squared up to ar to the n minus 1. And we want to find some nice way of simplifying this so that we can take the limit, because remember the definition of the series or the infinite sum is the limit of the partial sums. So we need to find a way to simplify this. And there's a trick that is not at all obvious, but let's anyway see the trick, because even though it's not obvious, it's beautiful. If we multiply both sides by r to look at Rsn, every term gets multiplied by r. So the a becomes ar becomes ar squared becomes ar cubed, and so on for all the terms in the middle. A to the n minus 2 becomes a to the n minus 1, a to the n minus 1 becomes a to the n. So we just multiplied everything by r. If it was true before, then it's still a true equation. And now let's subtract the top minus the bottom and see what we get. So if we look at Sn minus r times Sn, we're going to be left with an a, which does not get cancelled because there's no a on the bottom line. But the ar, we have ar minus ar, and we have ar squared minus ar squared. We would have ar cubed minus ar cubed. So a lot of the terms are going to cancel. Up to ar to the n minus 1's cancel, ar to the n minus 1 minus ar to the n minus 1. But then the first line does not have an ar to the n, whereas the second line does have an ar to the n. So if you subtract them and you're diligent with the cancellations, you will get a minus a times r to the n. And now it's a much simpler equation. We can try to factorize and solve for Sn. Right, if we factor things, we get Sn times 1 minus r. We pull out the common factor Sn. And then on the right side, we pull out the common factor a. We get a times 1 minus r to the n. And we divide both sides by 1 minus r, as long as that's not 0, as long as r is not 1. We get the Sn is a times 1 minus r to the n over 1 minus r. So here is the sum of the first n terms of a geometric series. So a 1 minus r to the n over 1 minus r. And then remember, to calculate the infinite sum or the infinite series, we are supposed to take the partial sum and then let n go to infinity. So we have to take, this is our partial sum, we want to take n to infinity. The only thing on the right that depends on n is r to the n. So we have to remember what happened with the geometric sequence, r to the n. And we said that this converges to 0 if r is strictly between minus 1 and 1. So if r is strictly between minus 1 and 1, this is going to become a 1 minus 0 divided by 1 minus 0. Okay, it will be a divided by 1 minus r. And what happens if r is equal to 1? If r equals 1, we go back to first principles. Then our series is just a plus a plus a plus a plus a, and so on. So just like before we saw with the sum of 1, it's going to diverge as long as a is not 0. Okay, so just to summarize, here is the important result that we're going to need and probably use many times. The geometric series with first term a and common ratio r, it converges to a over 1 minus r, as long as r is strictly between minus 1 and 1. Another way of saying that's the absolute value of r is strictly less than 1. And otherwise, it's going to diverge. And one thing I want to comment on here is that sometimes the left side can always be written in different ways. So you could start, say, with ar to the n from n equals 0 to infinity. So sometimes it's going to be kind of hidden. But if you think a series is geometric and you write out the first couple of terms, then once you write out the first few terms, you can pick out straight away the first term is the a, and the r is the ratio between a successive term and the previous term. So you can always find the a, find the r by writing out the first couple of terms, even if the sigma notation is written slightly in a different way. Okay, and one important special case that we'll use later is if we sub in a equals 1, r equals x, we get the sum of x to the n minus 1, but I want to write that as x to the n, provided I start at n equals 0. The sum of x to the n, which is 1 plus x squared, this is geometric with first term 1, common ratio x. This converges to 1 over 1 minus x, as long as the absolute value of x is less than 1. And right now, this is just for as a curiosity, but later, another way to think about this will be that the function 1 over 1 minus x has been represented as a sum of x to the n. So not as a polynomial, but as a kind of infinite polynomial or as an infinite series. And later we'll use this to find series for different types of functions just by playing around with the x and doing various operations. Okay, so here's another example with geometric series. So say we have 5 minus 10 over 3 plus 20 over 9 minus 40 over 27. And we're told it's geometric. How do we find the sum? Well, we have to figure out the first term a, the common ratio r, and then it's just going to be a over 1 minus r, provided that it converges. So provided r is strictly between minus 1 and 1. Okay, here the first term is 5. What do we have to multiply 5 by to get minus 10 divided by 3? Okay, that's minus 2 divided by 3. Right? If we multiply 5 by minus 2 over 3, we get minus 10 over 3. And then if we double check, so we're saying the ratio is minus 2/3. If we do 10 over 3 times minus 2/3, sorry, if we do minus 10 over 3 times minus 2/3, okay, we get 20 over 9, and so on. So this really is the common ratio. Okay, the common ratio is strictly between minus 1 and 1, so our series converges. It converges to a over 1 minus r, which becomes 3. Okay, so it's a pretty typical question. Maybe another kind of more involved question is, let's try to write 2.317171717. So the 17 part should be recurring as a fraction. So one way to think about it is to split off the 2.3, and then we have 0.017. So that's 17 over 10 cubed, if you stare carefully at the decimal points. And then each time we go across, we have another 17, which moves along by 2 decimal points to the right. So what does it mean to move along 2 decimal points to the right? It means that we divide by 100, or we divide by 10 squared. So each time we go from 17 over 10 cubed, then we divide by 10 squared to move along 2 digits to the right. We get 17 over 10 to the 5. We divide by another 10 squared to move 2 digits to the right. We get 17 over 10 to the 7, and so on and so on. So after the 2.3, it looks a lot like a geometric series. It is a geometric series with first term 17 over 10 cubed. And then to get the next term along, we multiply by 1 over 10 squared, right? 17 over 10 cubed times 1 over 10 squared is 17 over 10 to the 5. This times 1 over 10 squared is 17 over 10 to the 7, and so on. So we have this first piece, 2.3, that's just kind of separate, and then the rest is a geometric series. We know the first term, we know the common ratio, we can add it up. It adds to a over 1 minus r, which is 17 over 990 if you do the borrowing algebra. Okay, and then 2.3 is 23 over 10. So we have 23 over 10 for the first part, 17 over 990 for the infinite recurring part. We find a common denominator, we add them together, we simplify, super boring, but you can do it. You'll get 1147 over 495. So this is one application of simplifying these recurring decimals and writing them as fractions. Okay, maybe one more, finally, the strategy for calculating sums when we can actually find the partial sums is telescoping sums. So telescoping is kind of a general phenomenon of when you have the partial sums, if you write out the terms, you get a lot of cancellations, and you can simplify the partial sums into something that's easy to take the limit of. So here, for instance, does the sum of 1 over n times n plus 1 converge or diverge? If you just write out the terms, starting with 1 over 2 plus 1 over, let's think 1 over 6 and so on, if you just write out the terms naively, it doesn't help at all. It's very difficult to see what happens. But one thing we could do is to write an alternate form using partial fractions. So if we think of this as 1 over x times x plus 1, you could use partial fractions to write it as 1 over x minus 1 over x plus 1. And there's nothing different here if we just replace the x by I or by n. We can still write it in this different form. So we want to investigate the partial sums, the sum of the first n terms. Notice if we're summing up to n, we can't then use the n for the index that we're summing over. We have to shift that to I because we don't want to use n for different things. So we have the sum of 1 over I minus 1 over I plus 1. And now let's try to write out the terms. With n equals 1, we are going to get 1 over 1 minus 1 over 2, which is the first term. With n equals 2, we are going to get 1 over 2 minus 1 over 3, the second term. With I equals 3, we have 1 over 3 minus 1 over 4, and so on, up to the last term we sub in I equals n, we get 1 over n minus 1 over n plus 1. And then the beauty here is that a bunch of terms are going to cancel. We have minus a half and plus a half, minus a third plus a third, minus a quarter, and there is a plus a quarter in there, minus 1 over n plus 1 over n. All these terms cancel. We're left with 1 from the first term and minus 1 over n plus 1 from the last term. So now we've actually been able to compute our partial sum. It's 1 minus 1 over n plus 1. And now we can take the limit, right? Remember the definition of the infinite series is the limit of the partial sums. The limit of the partial sums in this case will be 1 minus 0, which is 1. So the series converges to 1. Okay, that's enough for today. So the important part is we defined what an infinite series is. What is the sum of an infinite series? It's just the limit of the partial sums, where the partial sums are the sum up to the first n terms. So to add infinitely many terms, we add n of them, and then we let n get larger and larger and take the limit. And then we studied a couple of important cases. So maybe we're given the partial sums, we just take the limit. Or geometric series are an important special case where we can compute the sum. Or telescoping series, because when we compute the partial sums, a lot of things cancel and we can find the limit. Okay, that's all for today. Thanks everyone. See you next time.